homework for Unit 9, and I think the key is up already, but the key is from previous years. So if you come to me with questions, I may act like it's my first time seeing that problem in a few years, because it will be my first. Like I didn't just make the key, which is what I normally do with your answer keys. But still, please feel free to come to me for help. In fact, I think like previous years, I used to just make like do half the problems for the key rather than the entire thing. So you may have questions about how to do some of that. And if you look at the very back page of the homework, it's an old quiz that I gave, like the Unit 9 quiz 1 or whatever it says. So that's a good like if you treat that like a quiz and you're like, I'm gonna try to not use notes on this, then you can see where you are on how much you understand about Unit 9. And then when we finish Unit 9, I'll give you guys the test, like the Unit 9 test. But I might just have you grade your own. Not for a grade, but just to see where you're at and all that stuff. But again, to your benefit to treat it like an actual test and see how much you know and how much you don't. But a lot of the stuff on that Unit 9 test and on the AP test that comes from Unit 9 comes from this section that I'm about to teach you. But first, remember we didn't finish this one, so let's do it real quick. This will be a good reminder of yesterday's stuff, yesterday's material. Okay. This says that a circle of radius 1 rolls around the circumference of a larger circle of radius 5, it says, but that doesn't seem right. But we'll talk about it later. And then it says the epicycloid traced by a point on the circumference on the smaller circle is given by those parametric equations. And then it wants us to find the length of this like flower looking thing. It's called an epicycloid apparently. Okay, so if that was too many words, what's happening is you don't have to draw this, but just so you understand, there's this big circle, which I think should say radius of 4. There's that big circle. And then there's a little circle of radius 1, like that. And they're taking a point on there and they're tracing it. That point right there. They're tracing it as this blue circle rolls around the black circle. And apparently that's the shape that it made. Conceptually, you good on that? Okay. Then they just want to know how I'm going to get rid of all my drawings now so that we can focus on the ones that are there. They want to know how long this line is, this curve is. So get that length. Okay. And if you were here yesterday, then you might remember, in fact, if you just look at this one, you might remember that all I have to do is use this formula, dx dt squared plus dy dt squared. So it won't be as bad. Like this problem seems like, whoa, this is crazy impossible, but it's not actually that hard. The hard part, the only hard part, is finding out the bound. Like from where to where do I go on it? So I want to get into today's stuff. Otherwise, I'd have you think about this. But the idea is that if I just find out, because if I just look at these equations and I have no idea, like where is this point 0, 4? Like how am I gonna find out like where to start this in terms of t? You know what I'm saying? Like where did this start? Did it start right here? Did it start right here? Did it start right here? Did it start right there? I don't know. So that's why I'm saying I'm gonna take t equals 0 and see where it was at that point. So plug that in. If t is 0 and x and y are the following, x would be 5 times sine of 0, obviously, minus 5 sine of 5 times 0. Like that. And then if you're good at your unit circle, then you know this is 0 minus 0. And then y would be at 5 times cosine of 0 minus cosine of 5, 0, or 5 times 0. Which would be 5 times 1 minus 1, which is 4. In other words, when t was 0, it started at that point that I had drawn before, this blue point. Cool. Then, again, this would be more interesting if we had a lot of time and that I had you think about it and you could think, what would I do after that? But you kind of you have a lot of options. I just thought of more other ways to do it as well. Like you could maybe your idea is just to be like, this doesn't look like it should repeat until 2 pi, which you might be right. But I'd have to think about it real hard because this is repeating every like more often than 2 pi. So anyway, you could think about like where the end of that would go. But what I did next is I said, okay, what about when would be this point right here, 4, 0 instead of 0, 4? And then if I can just find this length of what I'm highlighting right here, then I can just multiply that by 4 and get the length of the whole thing. So, I mean, that's a little bit hard to do. But what I did is I said, okay, I need x to equal 4. In other words, I need this equation to equal 4. And I need this equation, the y equation, to equal 0. So I need 5 cosine of t minus cosine of 5t to equal 0. Okay, but if you look at either one of these are very these are not very intuitive to solve at all. Like I don't have a great idea of how to solve, especially this one. That seems hard to do. But this one, at least it's at 0. So I can try to think of where 5 times the cosine of t will be equal to cosine of 5t. But that's very, very hard. One way that I could do it, though, is if I make both of this guy and this guy, if they're both 0, then 0 minus 0 is 0. So what I said, so I thought, and I was like, oh, okay, maybe. If t is pi over 2, then that would make this 0, and that would make this 4. The short version is I'll let you think about that on your own. Like, I don't think this problem is super, super, super important that you understand all the details, especially because I'm trying to get to today's stuff. And I said, but, you can take my word for it that pi over 2 would be the first time that this touches the x-axis. So what I'm saying is if I go from 0 to pi over 2, I will get that highlighted bit. This highlighted section of the like little flower thing. But I need 4 of those since that's only 1/4 of the actual little flower. So I just took this and I multiplied it by 4. And then I let my calculator do the work, put that integral into my calculator. And oh shoot, I guess we haven't found the derivatives of each of those. You know what I'm saying? Like I need dx dt, I need to square it, and I need dy dt, and I need to square it. And then I'll take that integral. And then that will be my answer. All right. Not sure if that's super worth our time, so let's just do it fast. If you're confused, I'm not that worried about this problem. So don't worry too much about it, but let's just get it done. We've started it, now let's finish it. So dx dt to put into here would be the derivative of that x equation, which is not too bad. Hopefully you said that. 5 cosine of t minus cosine of 5t. right?
No.
Wrong, because why? Yeah, chain rule 5t in here needs to be like that's a chain rule. So derivative of the sine is cosine. Derivative of the inside function 5t is 5. So multiply that by 5 right there, in case you forgot. And then dy dt is is the derivative of this guy, which would be negative 5 sine of t minus negative, so plus 5 sine of 5. And then I don't even want to write an extra step. Let me be lazy and say this blue goes in this blue and this red goes in this red. And tell you that if you put this into your calculator, you get an answer. I think you get 40, if I remember right, which is pretty crazy. You would think there's a pi in there or something, but not according to these calculators. Equals 40 finally. Okay, again, if we had more time, this would have been a more fun problem. You can think harder about where's this point, where's that point, or do I want to do 2 pi, or does it ever repeat before? Like, does it touch this point before pi over 2 or whatever? It's fun to think about this problem, but like I said, I think I want to get into today's material more than I want to spend time on this problem. But if you want to spend some time on it, like I can talk to you long more. But like I said, more important is today's material called vector valued functions, which are just basically parametric equations, just written different. So this is a cool one because well, first of all, it's on the test very, very often, like almost guaranteed it's on the AP test. Although last year they strayed away from that, but I will talk about that later. But outside of the AP test, it's also just kind of interesting because the motion that you guys have seen in AB is just like straight line motion like this. But most things in the world don't really move like that. You know, they move like not on a straight line like this in 2 dimensions. And so that's what these vector valued functions are good for. Is if I do that exact thing I was just doing, like that, and I keep doing it, you could break that down into, well, vertically, you're just moving from here to here, and horizontally, you're just moving from here to here. And if you put those together, then it will look something like this. Like you put them together in the right way, and then you get the motion. So that's what these vector value functions are good for. That's what this little paragraph says. Is oh, here it is. Here it is. A vector. No, I'm wrong. Somewhere on here it says that things in real life move vertically and horizontally. I think it's actually on the next page. But here, what this says is just getting you used to vectors. I don't know if you've seen vectors before. You've seen these? One person said yes. Other people don't remember. Okay, vectors, all they are is like a point. So here's me acting like you've never seen these before. It says a vector is an ordered pair, A comma B, and it has these sharp brackets like that. A comma B. They're like angled brackets. You see it right there, but just to make it very clear, there's them bigger. Actually, that's one of the many ways to draw vector brackets, but these are the ones that I've seen the most on the and it says the main difference between a point and a vector is that we think of vectors as arrows instead of points. So they carry some sort of like length and strength. Like if you were in physics, then you probably see a lot of vectors. where like the length of this tells you like how strong a force is or whatever. All right. So this would be the 0.24, obviously, but this would be the vector 24. Whoop, whoop. More on vectors later, but that's the basic difference between a point and a vector. But like I said, another difference between a point and a vector is that a vector you can think of as the whole arrow, meaning it would have a length, which is what we call magnitude. So it says the magnitude of a vector is simply the vector's length. And the magnitude is denoted with the absolute value bar. So if you get told get the absolute value of a vector, that means get the length of the vector, or the magnitude is what it's called. And sometimes to make it really clear so that you don't think its absolute value is and just make it positive, they'll put double absolute value bars, but you'll see it both ways. I use just the absolute value bar for reasons that you'll see later. Okay. So here, let me ask you something real basic. If I were to ask you to get the length of that vector, how would you do it?
Right there.
Yeah. You just make a little triangle. It's 2 over and 4 up, so 2 squared plus 4 squared equals the length of that. That's what this little formula says. It says to find the magnitude of vectors, use the formula x squared plus y squared plus square root of that. That's the Pythagorean theorem. Cool. All right, that will be important in many different contexts. But here on the packet, first, I just get you used to it. You won't get asked this on the AP test, obviously, because it's so like basic. But you will get asked it in, like behind, like you'll see how, like in context of a moving particle, you will get asked. So here's us getting used to the idea. The magnitude of 3, 4 would be v squared plus 4 squared in the square root. And I guess you could leave that, but this one is nice enough that you could calculate that. That would be 9 plus 16, which is 25, which is the square root of that square. Boom, that's the length of that vector. All right. Have you seen this before anytime? Magnitudes of vectors? That looks like a no. People are just staring. Okay, well, hopefully you get used to it fast. If not, it's kind of hard maybe to build up an intuition on vectors, but I'll try to show you visually what's going on with each of these vector like equations, stuff like that. All right, magnitude of this one, same thing, would be 25 plus 4, 5 squared plus 2 squared, which is 29, square root of 29. And then magnitude of this one, I mean, you can kind of just think about it, because it's just a horizontal vector with a length of 1. So you could just think of it intuitively and say that length is 1, or you can use the formula and see that that's the square root of 1, which is 1. Cool. All right, so magnitudes are lengths of vectors. Then another difference between vectors and points are, first of all, again, vectors are arrows, so they have a length, but also they can act on each other. So what I mean is you can add 2 vectors. And in math, all you need to know about adding 2 vectors is that just like you add the x coordinates and you add the y coordinates, and that's how you add. So that would be, in this case, 2 plus -3, or well, let me write my work. 2 plus -3, 10 plus 11. So this would be -1, 21. Cool. That's the sum of 2 vectors. If you're in physics or in any sort of science that uses vectors, then you know what that means is that, like, you had a force going this way and a force going this way, then the result would be something like this. Or actually, I mean, I'm not a science expert, but I'm pretty sure that's how they use them in physics. And what would that look like in a picture? It would be like if you took the vector 2, -3, 2, 10, which is 2 over 10 up, so something like this. Say that's let me call this vector A, vector B. You don't have to draw this, but just so you see what's going on. You took A and then you stuck this on the end of it. Like you took a force that went that way, then you took a force that went that way, negative 3, 11. Negative 3, 11. I took this blue vector and put it on this on the end of this, whoop, then the resulting vector going from here to here, that's the negative 121 that we got. Cool. All right, all of that is just not even calculus. That's just like me getting you used to vectors as best as I can in one lesson. But how you're going to see it in calculus is that you'll get vector valued functions. So not the vector 210, but the vector function comma function, for example. And like I was saying, this is what I actually wanted to say, or this is what I was thinking of when I was introducing the idea, is that when objects move in 2 dimensions, they move both vertically and horizontally. And for that reason, you can use parametric equations to break down the movement of 2-dimensional like objects. So break it down into what's it doing like on a straight line vertically and what's it doing on a straight line horizontally, and see if you can combine those to make some sort of like real 2-dimensional movement like this. Let me move my charger before I trip on it. Okay. Cool. All right. That idea of breaking it down into vertical motion and horizontal motion, that should not be new because that's exactly what parametric equations were. Like if you look back at the last 2 sections of notes, that's exactly what we've been doing. So there's nothing new here. The only thing that's different is that instead of them telling you, look, here's 2 equations that you're supposed to take together, they just write it as a vector. So instead of x of t equals function and y of t equals function, they write it like the vector x of t comma y of t. Actually, if you were here on when we did 9.1, like on last Friday or whatever, the way we graphed these equations on Desmos is to just put them in an ordered pair like this. So maybe this doesn't feel new to you because you saw that already as I've graphed things on this. Cool. Okay, then I looked up on the internet of the visualization of a vector function. I don't know if this will help you or confuse you more, because you're totally safe to just think of the actual graph itself. But what this is saying is that if for a vector function, instead of thinking of this point as like just a point on the graph, you think of that point on the graph as like a vector going from here to there. So every point on here, you're thinking of it as an arrow pointing from the origin to that point. That's why they're called vector value functions. But again, you're totally safe just thinking of these as normal functions, like normal points x comma y in this class. Okay, so that's an intro to vectors, like a quick crash course on vectors, what you need to know about vectors before we actually start to help you. Questions on vectors? If you had never seen them before, then I'm sure you have you have no idea what I'm talking about. In which case, let me just tell you that you're good to just ignore everything I said about vectors and just think of them as points. But if you've seen vectors before a little bit, then you kind of get a better understanding of how vector equations work and why vectors are different than points or whatever. But like I said, if you've never seen them, just think of them as points. Okay, Last chance questions before we do calculus. Okay, well then here's the good news is that doing calculus on vector functions is very, very easy. It's like it's exactly what you would hope it would be. The three main ideas in calculus, as you've seen, is limits, derivatives, and integrals, and all of them work as you would hope. So what I mean is, if you take the limit of a vector function, you just take the limit of the x, the limit of the y. The derivative of a vector function would be the derivative of the x, derivative of the y. Integrals, same thing. So that's at least good news. You don't have to think of, it's not like this crazy rule where the x and the y interact in some weird way. You just think of them as separate functions and put a comma between them. So here's a few practice problems. It says take the limit of this vector function as t goes to 3. Okay, like I said, that would just be, maybe I show my work good for this one. That would just be the limit as t goes to 3 of this first function, comma, the limit as t goes to 3 of that second function. Okay, and then you just take these two limits separate. So the limit of this first one, I hope you guys remember that if you just, your first go-to way to take limits every time is just to plug the number in, and if you don't divide by, oh hey, what's up, Glover? If you don't divide by 0 or break some sort of math rule, then you're good. Like that's your answer, which is what will happen here. E to the 6 is not breaking any math rules. So there you go. There's your limit for that one. But the limit for this one does divide by 0. You'd get 0 over 0. So let me check how much you guys remember from unit 1. Is remember how to take this limit?
Tested on both sides.
No, because you'd still get 0 over 0 or something. Approach 0.
Cancel the t minus 3.
Yeah, more like that's what you want to do. If I had gotten like 3 over 0, then yeah, test it for both sides. If you get 0 over 0, probably this limit exists, just something needs to cancel. So you actually got a couple options. What were you thinking, James?
Just like factor the top.
Yeah, if you factor the top, then the t minus 3s will cancel. The other option would be to do L'Hopital's rule. 0 over 0 is one of the times where you can do L'Hopital's rule. In fact, that might be quicker. Just 2t over 1 might be faster. But let's go with the factoring, like James said. Limit as t goes to 3 of t minus 3 times t plus 3 over t minus 3. So these guys cancel. And then the limit as t goes to 3 of t plus 3 would be 3 plus 3, which is 6. So final answer, I get e to the 6 on that 6. That's my limit. All right, and then now it's 8:40, so I don't want to rush through the rest of this, especially because what's coming up is the important bit. It's this motion type problem. So I don't want to rush through it. Let's just stop there. Not tomorrow, not Wednesday. No class tomorrow. I have meetings on Wednesday. So I'll see you Thursday and do this.